As demand for marine renewable energy increases, we are pushing further out into the sea to reach stronger and more stable wind streams. The further out we go, the deeper the sea becomes, making bottom-fixed structures unviable. Floating wind turbines therefore become a necessity. Today, most bottom-fixed offshore wind farms are connected in a daisy chain architecture. The widely used radial configuration is based on a string of 5 to 10 turbines. Each cable section must withstand the power generated by all the turbines upstream, so they must be designed to support a high electric current at every point. This architecture can also lead to production losses if a fault appears in a cable. To avoid this production loss, we can add a cable to link the last wind turbine directly to the substation, thereby creating a loop configuration, which allows the production to be rerouted to the substation in case of a failure. However, this increases the size and length of the cables and ultimately increases the capital expenditure. While these architectural solutions might be sufficient for bottom-fixed farms, they are not as effective in floating wind farm configurations, which require the use of dynamic cables, a relatively new technology prone to fatigue and external damage. As such, new innovative architectures need to be developed that both minimize the risk associated with dynamic cables and offer a cost-effective means of reducing production losses. At SuperGrid Institute, we develop subsea equipment to make future floating wind farms more reliable and financially viable. We are currently working on smart hubs for the Fishbone architecture. Each dynamic cable needs only withstand the rated power of one turbine, making the cable design and manufacturing simpler and cheaper, while relying on smart hubs to reduce production losses. We have proven this architecture to be the most efficient solution for the majority of upcoming floating wind farms. Our conclusions are based on our techno-economic analysis methodology, developed to compare grid architecture. This method accounts for capital and operational expenditures as well as expected production losses. In one of our studies, when compared to a radial design, the Fishbone architecture presented an estimated 10% reduction in CapEx, a 25% reduction in OpEx, and a 25% reduction in production loss. We believe this architecture is the future for floating wind farms and are dedicated to developing the technologies needed for this innovative solution. For more information about our work, come talk to us or visit our website.